Thank you very much. I appreciate the opportunity to be here and speak to you about a topic which I have been interested for at least a couple of decades. Energy storage is critical to everyday activities of our lives. It powers our smartphones, which keep us all connected. It also powers some of the appliances that we use in our household. And there are many, many applications for it. We need energy. We need energy to sustain global population, 7 billion people. They have to be provided with the energy. We have been using conventional energy, primarily fossil, and they are being depleted. While nature has taken millions of years to synthesize fossil energy sources contained in the planet Earth, mankind will use them up in coming decades. And here is something that we can debate about, whether it's going to be 10 years or 50 years. But eventually, we will use them up. And then there are environmental consequences and CO2 emission, global warming, climate change. So the environmental consequences of fossil use are serious. What do we do about that? We have to realize that we still need energy to grow crops, to heat and light homes, provide transportation, power electronic devices, and sustain our lifestyle. So this is just to get you started. We have been thinking about this energy problem, and a lot of thinkers, philosophers, politicians have been paying attention to it, and there have been considerable amount of work. And here I have some conventional fuel. There is a term which is floating around in the literature. It's called energy return on investment, EROI. And what it basically means is the energy out divided by energy in. Every energy source that we use, it takes a certain amount of energy. So if we look at some of the conventional fuels, for example, gasoline, it's 16. And then there are other fuels which are being developed. And you can see that ethanol from corn is 1.4. Now, 5.5 is a kind of minimum EROI to sustain industrial society. What does it mean? If we push for these sources, we have to subsidize them. And if we have to subsidize ethanol from corn, we have to take money out from some other sources from the economy, for example, education or research. So you can see that some of the things which are being talked about may not have much merit. So let's move on to the fuels that we use for transportation. Now we are going to focus in on to the transportation. And here in this table, I have miles per gigajoules. This is the miles one can get per gigajoule. You can see that from gasoline, we get about 3,600 miles. When we go to ethanol, it's 300. It's quite bad. And then right in the bottom, we have electric car running on US grid electricity. And you can see that this is 6,500. It's quite impressive. And this explains why there is so much of interest in electric vehicle and electric transportation. Now, if for the time being we ignore how we produce electricity, this electric vehicle makes a lot more sense. However, we have an option. We don't have to use dirty coal to produce electricity. We have alternate and sustainable energy sources. And these could be solar and wind. And this reminds me of a conversation I had with a friend of mine about maybe 7 years ago. I told him then that, look, this should be looked at. This seems to be very interesting. And he said, these are all feel-good technologies. And I said, Well, at that time, the solar was some 1% and wind was 2% and something like that. I said, that may be true now, but if it is nurtured and developed, it could be significant. Right now, I think the world energy or power generation from these two sources are over 5%, approximately. This is a crude number. And it's coming up. There are 100 countries in the world who produce electricity from solar and wind for commercial purposes. So these are not simply we can ignore it. But with these, we have intermittency issue. Now, if we add energy storage system with these alternate energy sources, we have a very viable system. And that's what a lot of people are working, a lot of countries are working, and use these two together to form a microgrid. And this microgrid could be of the size of a large hardware store or a large gas station. And this could be the distributed power or retail power centers where the batteries for automobile could be charged, could be bought, replaced, or the batteries or power sources could be rented for many other applications. So this is the model. In fact, it's being tried in some countries in Asia. These microgrids could be connected, such as internet, to make it a mega grid. Now, who is going to tell me about the time? Oh, you are. Good. I have some time left, right? OK, so let's zoom in on to energy storage. Energy storage is a very active area right now. There are technologies, but they are not good enough. We are looking for high-performance systems. So how do we define high-performance systems? First of all, they have to be safe. You may recall what happened with the Boeing aircraft battery a few months ago. So they have to be safe. They have to have high energy and power density. Energy density means how long a battery can last. If I have to replace or recharge my battery for my cell phone once a day, if it could be done once a week, I have increased the energy density by a factor of 7. Similarly, power density relates to how quickly we can draw current from the battery. So this is the second important factor. And then, of course, cost. It has to be really cheap. It has to be dirt cheap. So when we combine these three factors together, that's what gives high-performance battery. And we have been working on it. A brief outline onto the historical development of battery. There are two technologies which have similar chemistry, science, basic science, the batteries and the fuel cells. In the fuel cells, the reactants are flowing in the battery. They are contained. There have been attempts made to make hybrids of batteries and fuel cells. And here are some of the things that have been done in the last 30, 40 years. We have focused on to the solid-state rechargeable lithium-oxygen battery. Why solid-state? I said it has to be safe. The solid-state battery gives you the safety. It has been known by the battery people that liquid is the origin of all the fires and all the problems with the batteries. So that's the reason we have focused on to the solid state. Then lithium oxygen. Why lithium oxygen? Lithium oxygen gives theoretically the highest energy density. And so this is important. We started our activity a little earlier than 2010. We have our first paper published in 2010. So that's the reason we have that number over there, 2010. OK. Just few words about a lithium oxygen cell. We know about the hydrogen oxygen cell. It was discovered in 1839, so it has been there for a long, long time. In the periodic table, lithium is just under hydrogen. So a lot of people thought that if we could use lithium instead of hydrogen and get some power out, it would be nice. So that was number one reason, because explosive nature of hydrogen and the gaseous nature of hydrogen, and lithium being solid, it's a lot more easier to deal with. The second important benefit of using lithium is that lithium could be used as anode itself. In the case of hydrogen, a metallic structure has to be provided, doped with precious metals, for example, platinum, to act as anode. In this case, lithium could itself be used as the anode. Now, this remained in the textbook for a number of years. Then the proof of concept came along in 1996. But making a lithium oxygen cell, there were some technical barriers, and these are some of the technical barriers mentioned here. Lithium is very reactive, so it has to be contained, and the safety, as you know, as I discussed earlier, it's important. Then the conductive membrane, I'm going to go over it just in a minute or so. Then the lack of efficient air cathode. We need to have a cathode which can carry on the electrochemistry, and then move on to the next one. So this is the first time we put together a cell. A cell has basically three components: anode, electrolyte, and cathode. Before we got into this, we were working on the electrolyte for a number of years, and you can see that we have three layers of electrolyte, because one layer has to be provided to take care of lithium, and the other layer to connect it with the cathode. So in this case, we had developed a material called LAGP, and I'm going to say a few words about it in the next couple of slides. Now, this may be threatening, but my intent is to just convey a couple of things. We have been working on it for a number of years. It does two very important things. It transports lithium within the cell at a rapid pace, from anode to cathode, cathode to anode. That's number one. And number two is it also can carry out electrochemical reduction of oxygen and evolution of oxygen. So these are the two very important attributes of this material, which allows us to make a large quantity of this material in the cell. And it's a sand-like material. It's a ceramic material. As you know, safety is very important. So if we load the cell with a lot of ceramic materials, even if we have fire, we don't have to worry about it. It's not going to propagate. That's all I'm going to say about this. Now, this is the proof that the LAGP material can carry out electrochemical reduction and evolution of oxygen. There are some peaks here, though those prove that LAGP material can do those things. In the lithium oxygen cell, there has been reports out there that we can take oxygen from the air, carry out the reaction, and draw the power from it. But taking oxygen from the air it creates its own problems because of water and carbon dioxide. So we have designed a sealed configuration where we keep the oxygen in the cell, and we carry out the electrochemical reaction in the reversible manner. Okay. Now, this is for charge and discharge. There is electrical efficiency, the average discharge voltage, and the average charge voltage. They have to be in certain ratio to make it a practical cell. That's what I'm showing here, some additional data. And the important thing here is that if we look at state of the art and cathode, this is the capacity, this gives the energy, and this is what we have, a factor of 10. And then the same thing we see here in the anode, low number here with the state of the art, and this is the potentially available energy or capacity from the solid lithium that we can get. And those are the components of our cell. Okay, so let me summarize, the energy storage system plays a critical role in the societal energy needs, deployment, and large-scale application of alternate energy sources greatly depend upon the availability of high-performance energy storage system. We have developed a solid-state cell design. We have worked on the materials of construction. The chemistry is attractive for producing safe, high-energy density rechargeable batteries. The distinguishing feature of the design is the solid-state cathode configuration using the material Lithium LAGP material that I talked about. The R&D efforts are in progress to improve upon energy and power density and cycle life of lithium oxygen cell. Now, a lot of people have helped to bring us over here. As I said, I have been working on it for a couple of decades. There are a lot of people who have helped us. I would like to acknowledge the support of UDRI for giving us the facility and developing the battery research lab.